So yeah, I mean, my presentation is going to be about the power of statistical learning applied to the proportioning of fiber reinforced concrete. Can everyone see my slides? Okay, brilliant. So yeah, I mean, I like the Henry's presentation very much, and actually he touched down on a couple of things that I wanted to. I was going to start my presentation talking about, and the first. Let me see. Yeah. So what I'm going to do is I'm going to talk about an ongoing project where I'm using, I'm making an intensive use of data science techniques in relation to the proportioning of fiber reinforced concrete mix. But before that, I'm going to start with a short introduction about the project itself. And even before talking about the project, I'm going to follow on a couple of things that Henry has already mentioned, because yes, there is a lot of terminology, and now I'm throwing a new phase here, which is the one about statistical learning. So yes, we have plenty of terms and plenty of overlap between data science, analytics, big data, or data mining, and then we talk about machine learning, artificial intelligence. So a few weeks ago, I came across this. So I don't know if you're familiar with Plato's allegory of the cave. This is more than 2,000 years old, and basically it was an allegory where it explained that the reality that we see is actually a projection of more pure concepts. And I thought that probably this would illustrate very well what society or users or expect when they hear us talking about artificial intelligence. So usually people think about sort of apps and about software, automated prediction, and that sort of thing. But I think it's important to realize that actually all of that, there is a lot of data science happening behind the scenes. And when we have the data and we have the power of all the data that we have accumulated, be it because we have repeated different, experimental campaigns, or because we have done a literature research, or because we have a repository of data adequately maintained, we're throwing onto those data a lot of statistical techniques to come up with models and so on. So that's what we are trying to do here. I mean, it's not, I'd like to call it statistical learning, because it's not only the machines learning, it's also us as designers, as engineers, learning from the data when we are processing those data. And that, in a way, is what this project called Optimization of Fiber Reinforced Concrete using data mining is about. It's a project that I lead and is funded by the ACI Foundation. And the articulating principle is to look at the proportioning of a fiber reinforced concrete mix as a sort of a multi-objective optimization problem, because we want to optimize different factors. We want to improve or to make the material optimum from the cost-benefit perspective in terms of compressive strength, in terms of flexural strength, and that's very important, but there's also the workability in terms of how placeable and how easy to place that mix is going to be, how stable, but also the free state properties. They also influence the compressive strength, and they also influence the flexural strength properties and the variability of these properties. So in a way, all these dimensions, all these 3 dimensions, plus the intrinsic variability of the material, are 4 dimensions that need to be approached as a multi-objective optimization problem. So it's a multivariate perspective, because we are going to be looking at different properties, and we want to take advantage of the correlations. Now, there is a sentence there that I say that variability is not a problem, but a source of information. And I think that's key. That's one of the key factors when you start talking about data science, because we are very used to papers where we generate our own source of data, and we have, like the collection of results from our experimental campaign. And then we are always saying, but yes, these are my results, but then if you compare this with someone else's results, then there might be some source of variation. And we tend to traditionally regard that as something to be careful about. Yes, you need to be careful of those things, but actually variability from different sources, it's actually a source of information, and we should be able to capitalize on that. Now, that's only possible when you have multiple sources of information, not just 2 or 3, when you have hundreds of them. And that's what this project wanted to do. The first objective was to compile a lot of information regarding mixed proportions and their properties from previously published papers, and then use that information to derive predictive models so that we could relate the residual flexural strength parameters in the case of fiber-reinforced concrete and their variability with the proportioning of the mix. So we can sort of statistically analyze all these 4 dimensions together in this problem, and we can derive some models that we can then embed in a software that can be used by the final user as a sort of optimization tool, but also as a as a sort of a learning or visualization tool in order to understand how the mix proportioning, the different FRC mixes work in terms of their properties and their variability. So the outline of the project follows more or less these objectives that are presented in the previous slides. And you can see here a flow chart, which is basically we dig up different papers that have been published and have information about the concrete mixes and their properties, and we put that into an organized, consistent, coherent database. So there's a lot of data mining and preparation going on in there to ensure consistency. We prepare the database, we clean it, and once we have the clean final version of that database, and we start analyzing to try to obtain models that can be used in prediction as well as quality control and interpretation of general trends. So the database that has been collected for this project has been organized as different variables in parallel. So we have some variables that I call the mixed proportioning variables, which are like the cement content or the superplasticizer, the type of fibers, the fiber content, length, diameter. So those are properties that define not only the relative amount of the different constituents of the mix, but also their main descriptors. What is, for example, the maximum aggregate size? What is the length and aspect ratio of the fibers? What is the type of SEM that you have in a certain mix? All those are mixed proportioning variables. And then for each of the cases, for each of the entries that we have in that database, we also have the variables related to properties. So we have the slump, we have the compressive strength, the residual flexural strength parameters. And I have organized, the database is organized in 2 data sets. So one is for steel fiber reinforced concrete mixes, and the other one is for synthetic FRC mixes. So as you can see here, we have nearly about 2,000 cases, almost complete cases of information regarding different mixes and the properties. So there is a lot of variability going on in there. And that's when you can start capitalizing on that variability to extract information. So that was a bit the introduction to the project and why I'm calling this statistical learning. And then in the next few slides, I'm going to show you a few examples about the modeling of the relationships between the mixed proportioning variables. Because the first thing that we need to do when we're doing data science or analytics, artificial intelligence, is to understand the data that we have. And therefore, before jumping ahead to the main objective of this project, which would be predict the properties of the mix based on the proportioning of the mix, I wanted to have a look at what the different types of mixes that I have in the database look like. Because we all know that, for example, when you increase the cement content in your mix, you're decreasing probably the aggregates content. And that sort of thing is something that we know. So it's important to make sure that all the models that we derive can sort of embed that knowledge within them. So this first step of the project was concerned with nothing to do with the properties of the materials, just focusing on the relation between the different parameters of defining the proportioning of the mixes and their main descriptions. And the objective was not only to model in terms of obtaining equations that can give me approximate coarse aggregate amounts or typical coarse aggregate amounts for a mix depending on the aspect ratio and the amount of fibers that I have, but also to develop plots and graphs that can be used to understand, to learn about the material. And the method, it's as simple as multiple linear regression. Now, this is again something that we don't talk about enough, which is the specification of the regression models. Regression is a simple tool for supervised learning, but I always say that it's very important to remember in statistics that all the models are false by definition because they are only models. Some of them are also useful, but they are also false. I mean, all of them. So the regression, when you're using software to predict information, it's always important to remember that it learns depending on how you specify the model. And that's key. So for instance, if we want to predict the compressive strength, we wouldn't use water amount and cement amount in the mix separately. We would use the water cement ratio because we know that that is the relevant parameter. So there's already a piece of semi-empirical knowledge that we have in our heads that the machines don't. And the specification of the models is important because we needed to try different alternative variables or constructions or artificial variables based on the information that we have in the database, looking basically at three objectives. One, and the most probably the one that focuses most of our attention in most of the time in practice, is the goodness of fit. So as Henry was saying, how well the model fits my data. But also, and Henry touched about that, and I think it's also important, it's not only the fact that we need our models to be good in terms of being accurate, we want them to be useful, we want them to be interpretable, so easy to interpret. So that's also key. And in terms of the robustness, we need to derive equations that are robust in terms of how they are going to behave when we use different data other than the information that we have used to derive the models. So looking at those three things, I started looking at different relationships that we could try and predict in the mix. And the first one is the coarse to fine aggregate ratio. Why? Because I thought that it's interestingly quite a good proxy to the grading of the aggregates in the mix. And that has a huge impact on the fresh performance, and is something that we don't think about enough when it comes to fiber reinforced concrete. If one plots the coarse to fine aggregate ratio in the data set, in the database, with respect to the gravel with respect to the coarse aggregate contents, you can see that there was a very clear correlation, suspiciously clear correlation, basically looking at the scatter plots. And it's also affected by the maximum aggregate size and the fiber material in the mix. So the regression analysis yielded these two very simple equations, which are actually very accurate, which are able to predict the coarse to fine aggregate ratio as a function of the maximum aggregate size, the coarse aggregate content, and also the type of fiber, obviously, because the equation is slightly different. And then you can start producing plots like this, where you can try and explain why the mixes vary in this or that way, or why the people that have proportioned these mixes have made those decisions of, for example, decreasing or increasing this parameter when we have different sizes of aggregates. Then, after looking at the coarse to fine aggregate ratio, it was also important to look at the total aggregates content. And rather than the total aggregates content, it worked better from the point of view of regression analysis in terms of producing more stable results, more robust models, the coarse aggregate content. And again, a regression equation was fitted to try and obtain the coarse aggregate contents as a function of the maximum aggregate size and the properties of the fibers in terms of their sizes and so on. And okay, fantastic. Thank you. And with this model, you can obtain, for example, very interesting plots like this, where you can see a little bit the trends on the trends that each, for example, this shows the coarse aggregate content depending on the fiber volume fraction and the fiber length. So there's different, I'm going to skip this part because I don't want to spend a lot of time, but there's different conclusions that you can obtain by looking at these contour plots. And again, this is related to the interpretability. And finally, we did the same with the binder content. So trying to predict the binder content as a function of the other parameters in the mix. And we obtained equations that were very, very accurate in terms of fitting the database. And again, it's important to remember that these R-squared values look high, but this is even more significant when you consider that you're probably you're talking about mixes obtained from more than 100 different papers produced by different authors, and they are relatively simple. So this is very powerful. But then in terms of the binder content, it was also interesting to see that the fibers were not in the equations explicitly, but again, they are not explicitly here, but the binder content was a function of the coarse aggregate content. So in a way, when we organize these three equations that I've just told you about, you have one equation which based on the maximum aggregate size and the size and dosage of the fibers gives you the coarse aggregate content. Then you have another equation that gives you the coarse to fine aggregate ratio. So based on those two parameters, you can directly obtain the sand content. And once you have these two, using the third equation that I presented to you, you can obtain the binder content. And you can see that the binder content affects the variables that affect, the fibers affect the coarse aggregate and sand contents, which in turn affect the binder. So yes, they are influencing the aggregate contents. Then I'm going to try to cover these slides in 2 minutes. So I'll probably skip a few of them because I'm conscious of the time. So the next step was obviously to try and relate those information about the proportioning of the mixes with the properties and focusing on the flexural strength only. It was, again, important to pay attention to the interactions between the different variables. And it took us quite a long time to get to formulate an equation like this. But basically, we have 4 different residual flexural strength parameters. We obtained the same format of equation for the 4 of them. And it's simply a matter of that for each of the residual flexural strength parameters, the coefficients in red in this equation are different. So basically, in one equation, we were condensing dozens of equations for different cases. And all of them can be plotted automatically. So for example, here you can see for FR1 and FR2, you can see the plots that show you the effect of volume fraction of fibers and the aspect ratio. So these are just a handful of plots that that can be generated from using these models and a few of the conclusions that I unfortunately don't have time to emphasize here. But I will finish with the closing remarks, because this was just a very quick example of what statistical learning can do for you. And it's not only that the equations or the software that we end up programming learns from the data, it's also that we need to enjoy the journey and use this process to discover and learn ourselves. So in the case of this project, which is an ongoing project funded by the ACI Foundation, the database of almost 2,000 cases has been compiled, and the regression analysis has yielded models that are useful to obtain accurate estimates, as well as very good tool to better understand the interactions between the different parameters. And unified predictive model for the residual flexural strength parameters is possible. And then using these models, obviously, you can optimize the proportioning of your mixes. So thank you so much. I'm sorry if I overrun a little bit, but there you have my email if you need to get in touch with any questions. Thank you.